We are starting the next section where we will finally discuss Euler's theorem. Euler's theorem is a generalization of this statement which we already have seen. This is our familiar Fermat's theorem. If p is a prime number which does not divide some integer a, in other words, if p and a are relatively prime, then the p minus 1th power of a is congruent to 1 modulo p. Euler replaces this prime p with any integer n, positive integer of course. And this is Euler's generalization of this statement. Let n be a positive integer and a be some integer so that they are relatively prime. Their GCD is 1. Then a to the power phi of n is congruent to 1 modulo n. Note that this is actually a generalization of this one, because if you put a p here, then what is phi of p? Phi of p is just p minus 1. Today we won't see the proof of this, rather we would see a lemma which is needed in its proof. We will see the proof in the next number theory video. And this is that lemma. Let n be an integer greater than 1 and let a be an integer relatively prime to n. That means the GCD of a and n is 1. Suppose a1, a2, etc. up to a phi of n are the positive integers less than n and relatively prime to n. We have phi of n here because as a suffix, because by the definition of the phi function, this is the number of such integers. That's why. If so, then you consider these integers, which you obtain by multiplying these integers by a. These are congruent modulo a to these integers in some order. The proof starts like this. Suppose two of these integers which are different are congruent to each other modulo n. That means suppose there exist I and j within this range of suffixes which are different. Say I is less than j, but such that aai is congruent to aaj modulo n. Then what are we going to get from this supposition? This is what we get, because a and n are relatively prime. So by the theory of congruences, you can cancel a from both sides, obtaining this congruence, that ai is congruent to aj modulo n. So this means n divides ai minus aj. Now what do we know about the integers ai and aj? Namely, they are positive integers, so greater than or equal to 1, and they are both less than n. Relatively prime to n also, but right now we just need these two inequalities. I mean, these four inequalities, rather I should say. And from them, we get these further inequalities. If you multiply this last inequality on both sides by minus 1, you get minus n less than minus aj. But minus aj is less than ai minus aj. Why? Because if you add ai to minus aj, you are adding a positive integer. So that means it will increase. So that's why this strict inequality. This one, however, is itself less than ai. Why? Because aj is positive. So if you are subtracting a positive integer from something, that gets reduced. If you don't subtract, then that means that is larger. And ai itself is less than n. So you find that this difference is strictly greater than minus n and strictly less than n. And at the same time, it is also divisible by n. Now, what are the multiples of n that lie strictly between minus n and n? Only 0. Nothing else. So that means this now has to be 0. So ai is equal to aj. But this is a contradiction, since I and j are distinct. I is less than j, but the point here is that I and j are distinct, and those numbers a1, a2, they are the numbers which are positive integers less than n, relatively prime to n. So they are distinct. So if I and j are different, how can ai and aj be the same? So that means our initial supposition must be wrong. So we write like this. So our supposition is wrong, i.e. these numbers are mutually incongruent modulo n. This means that if you choose any two different numbers from this list, they will not be congruent to each other modulo n. Now next we uncover something else about these numbers a.ai. What do we know? Our hypothesis is that a and n are relatively prime, and by our definition of these numbers ai, they are the integers, positive integers less than n and relatively prime to n. So they are relatively prime to n. So that is why, because of these two things, you go back and see the lemma preceding theorem 7.2, there you see that then their product, the product of a and any one of these ai's is also relatively prime to n. So these numbers which are mutually incongruent to one another modulo n, at the same time they are also all of them relatively prime to n. Now next we are going to concentrate on some number, some arbitrary aai. So for that we just fix some j in this range and consider the number aaj. For that number aaj, there exists a unique integer b which is non-negative, is less than n, and which is congruent to aaj modulo n. What is this b? This b is actually nothing but the remainder that you get when you divide aaj by n, and obviously that is congruent to aaj modulo n. Now by the first lemma of section 2.3, the GCD of b and n is equal to the GCD of aaj and n. It is that lemma, if you go back and see the statement, it's that lemma from where we get the Euclidean algorithm for calculating GCDs. That one where we do division again and again, that thing. But we already know that this is equal to 1. So we have now found that this b is relatively prime to n. Now this is an important observation. Note that since n is greater than 1, so b cannot be equal to 0. Why? Because if b is 0, what can you say about the GCD? This GCD will then be equal to n. N is positive, that is given. But how can that be 1? Because n is greater than 1. That's why b cannot be equal to 0. But what do we know about b? We already know that b is greater than or equal to 0 and is less than n. So b now becomes a positive integer because of this, which is less than n, and at the same time it is relatively prime to n. What does that mean? It just means that b is one of those ai's. So this is what we have. B belongs to this set. But aaj is congruent to b, so that's how any such aaj is congruent to one of these numbers. And you combine with this the fact that we initially proved that the aaj's, or should I say aai, because here we fixed j, those aai's are mutually incongruent to one another modulo n. So taking everything into account, you now have the claim that those aai's are congruent modulo n to these numbers in some order.